dispersive equations. I want to know that if it works, if it holds on locally symmetric space or not, and it involves some geometric assumptions, and it's based on these three objects. So let me start with the rank 1 case. Maybe start with the hyperbolic space. I know that the audiences are experts of symmetric spaces. I think I don't need to use too many time to record the definition. I just record the notations. So we know that there are different models of hyperbolic spaces. For example, we can use the upper half plane or the hyperboloid, but in both ways we know that we can write a hyperbolic space as a homogeneous space or as a symmetry space by two Lie groups. So I will start with the hyperbolic plane, then the n-dimensional hyperbolic space, then maybe the rank 1 symmetry space. I will recall the three objects we just saw in the last slides, how they relate with each other in rank 1. Then we will talk about what happened in higher rank. So the object to study is the L2 spectrum. We consider the Laplace Beltrami operator. Then we consider its spectrum. And we know that in the Euclidean setting, we know that the L2 spectrum in the Euclidean setting is purely continuous from 0 to infinity. But if we consider a lattice, a discrete subgroup, and we can get something else, then for example, in this case, Zn, we get a torus, and the manifold becomes compact. So the spectrum is purely discontinued. So we have discrete eigenvalues. But if we if we replace the Zn by Zk with k strictly smaller than n, we will get something different. For example, if we have a cylinder with a finite length, so we have for example, we have at the bottom we have compact parts. Then, but at the cylinder, we will have a infinite area. So the spectrum will be a little bit complicated. It's just want to say that depending on the discrete groups you choose, it will change the property of the manifold, or we will see it's the same phenomenon on a hyperbolic space. So we know that on a real hyperbolic space, so we know that it has also the Laplacian has also a continuous spectrum, but starting the bottom is no more 0, right? The 0 corresponds to the trivial eigenvalue, and then trivial eigenfunction, and the bottom of the L2 spectrum starts from lambda 0, which is -1 over 2 squared. So we have a spectral gap here. This is different than the Euclidean setting. So when we pass from a hyperbolic space to a hyperbolic manifold, so we have this. I will explain what happens for a hyperbolic manifold in dimension 2. This is what happens on a hyperbolic plane. But if we consider a hyperbolic manifold, it means that we consider a discrete subgroup of G of SL2R, and we get a new manifold. In this case, if we consider SL2J, we will get a hyperbolic surface which is non-compact, but with finite area. So in this case, we have a continuous spectrum as on the hyperbolic plane, which means that the bottom is 1/4. At the same time, we also have discrete eigenvalues, which we say that there are infinitely many eigenvalues. That unbound means that the discrete spectrum embodied in the continuous spectrum. It means that there is nothing from 0 to 1/4, which means we say that there is no exceptional eigenvalues. It is something here, we call it exceptional one, an exceptional eigenvalue. In this case, nothing here. So this corresponds to the Seilberger's famous conjecture on a general surface. But if we replace the SL2 SL2J by something else, we will get a different hyperbolic surface. For example, sometimes we call it thin group. If we consider something like gamma is a discrete subgroup of SL2R such that the volume is infinite, then in this case, we still have a continuous spectrum, but the bottom is no more 1/4. We can compute it, we will see what it is, but in general, it could be something else. And the continuous spectrum starts with this lambda 0. And in this case, all eigenvalues are exceptional, which means that the discrete spectrum is in the spectral gap. There are finitely many of them. So for us, the first question we want to ask is that what is lambda 0, right? We have to know what is the continuous spectrum. Then we can continue with the distribution of discrete eigenvalues. So the lambda 0 is just at the bottom of the minus Laplacian. It's the first, we can say it's the bottom of the continuous spectrum. We want to know what it is, lambda 0. Okay. Can you hear me?
Yes, we can hear you.
Okay, sorry, because I'm in the presentation mode. I cannot see the other screen. Sorry, so I just confirm. Yeah, okay. So to understand lambda 0, we have to introduce another notation, which is called the critical exponent. It means that if we consider, for example, a lattice in Rn, and we consider a ball with radius r.
Can you go back to the previous slide a little bit? Can you go back?
Yeah.
So this lambda 0 is the minimum thing, right? Okay.
Yeah, sorry, yeah, I forgot X
so
here. X is a hyperbolic space, or is a symmetry space. It's a symmetry space. Yeah, I start with H2 with two-dimensional example. Yeah.
Okay, thank you.
Yeah, it's the minimal. Yeah, it's the nth. Yeah. Okay.
Yes.
Yeah. So we go back to counting the lattice points in a ball in the Euclidean setting. And in the Euclidean setting, we know that if we counting the points in this case, the discrete points, it will grow polynomially fast. But on a symmetry space or on hyperbolic space, we know that which grows exponentially fast at affinity. So when we count the discrete points, it's exponential fast. So we add a log here, and we want to know what is the delta gamma. And this is indeed, it's the same thing. It echoes the infimum of all the parameters S, such that this series is finite, and this series is called a Poincare series. And this delta gamma is exactly the critical exponent of this series. Right? If it's S greater than this, and the series is finite, convergence, converges, and otherwise it will be infinite. So we know that, and I think you know the symmetry space. So this critical exponent is always greater than 0 and smaller than 2 rho. I mean, these 2 rho in our n-dimensional hyperbolic spaces is n minus 1. So in general, it's two times the norm of rho. We will see. And with this notation, then Strichartz and Paderborn proved first in dimension 2, like this characterization of lambda 0. It means that if your critical exponent is small, I mean this is from delta gamma is greater than 0, smaller than 1. If this on the the left half part, then the lambda 0 is 1/4. It means that in this case, the continuous spectrum of the hyperbolic surface is the same as on a hyperbolic plane. In this case, we say that the spectral gap is trivial. Trivial means that it has the same spectral gap as on a hyperbolic plane. But if the delta gamma is greater than 1/2, then the bottom moving a little bit on the left. In this case, we say that we have a non-trivial spectral gap, right? So thanks to this characterization, we know that if lambda 0 is 1/4, then the critical exponent must be small. So this is a very interesting relationship between two objects in different areas, and this was
what
extended.
happens if gamma is SL2Z, suppose? If gamma is SL2Z, SL2G?
If gamma is SL2G, it means that we have a finite area hyperbolic surface, and the lambda 0 must be 0. No, lambda 0 must be 2 rho. Wait.
And what will be the...
No. If gamma is SL2, then the delta gamma is 2 rho, and lambda 0 is 0. This is what happened on a finite volume hyperbolic surface. So what we are considering is gamma, the space is of infinite volume. We are considering this case. This is our what we are care about. Okay. I continue.
Yes, you can go.
Okay. So yeah. So this is on dimension 2, and so it was extended to n-dimensional by Sullivan, then to all symmetric spaces of rank 1 by Kohelet. So we know exactly the characterization like in rank, as in dimension 2. Just replace the 1/4 by rho squared. Right? In rank 1, we know what rho is just a real number. So we get the relationship between these two objects. But now we talk about the relationship with this L2. We say that it's tempered. Let me explain what means tempered. So when we consider the orthogonal decomposition of the L2 space, then in rank 1, this is very important. We know what is the GK hat, but only in rank 1. In this case, we know that it involves some different representations. There are 3 cases. And we say that L2 is tempered if this spherical unitary of G doesn't involve the last case, the complementary series. And in our case, we know that the volume is infinite, so the second case is also automatically ruled out. So in our case, we see that L2 is tempered. We see that this spherical dual of G involves only the unitary series. This is the definition, and we can get immediately this equivalence between these two things, right? Because from the right to the left, By definition, if L2 is tempered, it involves only these representations. So the lambda 0 is automatically rho squared. This is the easy part. So from the left hand side to the right, we know that if lambda 0 is rho squared, if L2 is not tempered, it means that this lambda should be purely complex. It becomes I lambda. Then it means that this thing will be smaller than rho squared, which violates the assumption. So in rank 1, we get very easy this equivalence. But in higher ranks, there is a problem because in higher rank, from right-hand side to left is also easy by definition. But from left to the right, we are not sure lambda is not always purely imaginary. It means that we cannot conclude as we did in rank 1. So this is a problem since long time. So we cannot get the equivalence like here. We get only from right to left. So at least we know that in rank 1, we know that this figure, this diagram is completely commutative, right? We have equivalence between these three objects. So our question is quite natural. We want to know what happens in higher rank. But this the setting is higher rank, but with infinite volume, because in as the audience asked, if we consider a lattice, if gamma is a lattice, equivalent say gamma x, this hyperbolic manifold is of finite volume, and then the delta, the critical exponent is automatically 2 rho. And what we know, we know what happens. So we want to know what happens for the infinite volume manifold, infinite volume locally symmetry space. So I think you are for the symmetry space. We use standard notation. So I just vastly recall the definition. It's just a complete manifold, simply connected with non-positive sectional curvature, and which grows exponentially fast at affinity, and we can write a symmetry space as G mod K. Right? I think this is the notation you know very well. And we consider in higher rank a discrete subgroup of G, and the G satisfies that the volume of this locally symmetric space is infinite. Here, another torsion free means that there is no finite order element except for the identity. With this assumption, we can guarantee that this locally symmetric space is still a Riemannian manifold with the matrix with structure comes from the symmetry space. So this is a general assumption. So the first, before moving to the result, I think I also need to recall the Beltrami, right? So we say that the symmetry space is of rank L. It's this Cantor subspace has the rank L. So we consider this. For example, we consider always example of the root system A2, the most simple but not trivial case, and then we do all the computations in the Beltrami. And yeah, and the last notation is we use this Cantor projection, which maps a function from the semi-simple group G to the Beltrami. And we use the notation mu as we call it the Cantor projection. It means that if we consider to the identity point, so the length of the orbit gamma is just the Euclidean space like mu gamma. Like we can project it to the Beltrami and we consider its length. So in higher rank, as we saw, we can characterize the lambda 0 by using the rho, right? If the delta gamma is small, then we know that lambda 0 is rho squared. In higher rank, rho is normal a real number. It's a vector. For example, here this is the rho axis. And I think you all know this rho is half sum of the positive roots counting with multiplicities. So the first is not the first, but the characterization is given by Jean-Philippe and me by using different, we call it the modified critical exponent. You can see that in higher rank, we can have almost the same characterization. We just put the norm on rho, right? Because it's a vector normal number. And it's almost the same thing than what happened in rank 1, except for we use this delta tilde instead of delta. So what is delta tilde? So it's not us who consider, from rank 1 to higher rank, it's a very, very natural motivation, and there are a lot of people studying this kind of generalization. So I think the first start it was made by Losanger, who he used this delta gamma. This is the same thing as in rank 1, except that in rank 1 this could in rank 1 there is no right there is no direction. It means that if you consider a variable in a Beltrami, in rank 1 you consider only the length but not the direction. But in higher ranks you should consider the direction with the inner product with some rules. But Losanger using this kind of definition. This is a standard. This is the direct generalization of the Poincare series to higher rank. You can see that this quantity can only measure the length but not the direction. So he gets only a lower and upper bounds of lambda 0, but not the characterization. So with Jean-Philippe, we introduced what we call the modified Poincare series, which means that the Poincare series equipped with a modified distance. And this just the difference is that in the original generalization, for example, with this distance, if we consider a ball, for example, if we consider a ball in of radius r, in A2, you can see the ball is just like that, right? Because I consider I consider the well-chamfered part in the well-chamfer. If you continue, there will be a ball, there will be a circle. But if we use this kind of distance, we will had body. We will had we call it the body hetero distance. We will have something like that, right? Like how to say that? Hexagon. So we just use this kind of distance and a little bit change. We can define this delta tilde. And delta tilde has a similar property as the original delta. It's a little bit smaller than this, and they are the same in rank 1. It means that it's a generalization of the original critical exponent. So with this notation, with Jean-Philippe, we give this characterization in higher rank. So first step, we prove the equivalence between the bottom of the L2 spectrum and this critical exponent of the subgroup of the discrete subgroup. It's just we say it. This is delta gamma. It's just sorry. This is yeah, the same thing. Sorry, this is a typo. It's critical exponent of some Poincare series, but it just reflects the way how we measure the discrete subgroup, how we measure the growth rate of the of the discrete subgroup. They are not the only way. You can see there is one way, like by the original way, and the other way, which also used a long time ago by Caron and Péton. And we will see there is the third way, right? So we just
can you go back to that result of yours, Shankar? So
here,
was
here.
previously. So you said that there is a error here. What is the error here?
Sorry.
Typo? So what is the
typo.
error?
It's here. It's a gamma. It's the same thing. It's a gamma, but here it's gamma parted. The brackets is just there's a typo here, right? Not just the typo, but the notation.
Okay,
Nothing.
so my question is, was there any relation? Was there any theorem like this in terms of just delta t, not delta tilde gamma? Sorry, delta gamma, not in tilde.
Sorry, you mean the delta gamma is large?
No, why you consider this delta gamma tilde instead of delta gamma? Just
Yeah. This
that is a question.
yeah, because I think if we consider this norm, you can only measure its length, but with this you can reflect the direction of the mu gamma, right? Because you consider the inner product. There is a you should take count of the direction of this element with the rho, right? This is we call it the polyhedral distance. Because we consider both the length and the direction. Okay.
But probably in one-dimensional case, you don't see that distinction because of everything is
In rank 1 they are the same, right? In rank 1 there is no direction thing. There is no direction problem. Exactly.
Okay.
So other progresses were made by Edwards and the famous mathematician He-Oh. They prove that this as I explained in rank 1, from the above to below, we can get it immediately by definition. But from below to above, this direction was a hard question, was a conjecture since a long time. And sorry, oops. So the first progress are made by He-Oh. They say that the gamma is unobserved. I don't want to explain what it is. I just want to say, because it's already known now, it works in general. So I don't need to explain what it means. Another subgroup, it's just a special, a particular class of discrete subgroups, which generalizes the concept of convex co-compact subgroups. For the convex co-compact subgroups, we will see what they are later. So this is unobserved is just a way to generalize this concept from rank 1 to higher rank. So they prove it that from below to above with this assumption, and this assumption was removed very recently by two colleagues, Weich and Wolf. They are Wolf was my collaborators on this work, and Weich is the boss of our group, and they were both in Paderborn, and they proved this in general. So in your world, it's just we have the equivalence now between the temperatures of L2 and this so-called P gamma. So what is P gamma? P gamma is what I said is the third way to measure the critical exponent. So this notation was introduced by Jean-François Gan. He wanted to generalize the Paterson-Sullivan measure from rank 1 to higher rank. Then he introduced this notation. This is another way to measure the Poincare series. It means that you consider an arbitrary vector inside, and you consider the open cones run over all the open cones containing this vector, and you have a new Poincare series, and not a new Poincare series. You should add this condition, and we have a new critical exponent. So they use this notation, and they proved the equivalence between the temperatures of L2 and this critical exponent. So this critical exponent is usually called the growth indicator function. So we already have the equivalence on the left and the equivalence at the right, and we want to know what happens in the middle, right? From right to the from the left to the right. It's also known now. So it's by Wolf and me. We show. We find the relation between our modified critical exponent and the growth indicator function introduced by Gan. We just give this characterization, and with this we can show the equivalence between this condition and this condition. It just simply says it just means that no matter you consider which critical exponent, if one is small, another is also small. This is like the smallness of the critical exponent. So with this equivalence, we can. So the whole diagram is now commutative, right? We have equivalence between every object. So on the one hand, we can give another characterization of the bottom of the outer spectrum, not using the modified critical component, but using the growth indicator function. But the best part is now we know now if the lambda 0 is a rho squared, we know this lambda 2 is automatically tempered. So this answers the question that I asked in the beginning. What happens in higher rank? At least say even although the critical exponents are more involved, a little bit complicated, but it's quite natural because when we go from rank 1 to higher rank, the well-chamfer becomes a higher dimensional thing, and the analysis becomes complicated. It's quite natural. So it's the same thing here. I mean, we use different kinds of critical exponents. We can establish the equivalence between each object. So why we studied and why we want to know if L2 is tempered or not. I mean, for the people working on geometry, they have a lot of motivations, and particularly people needs to use the representation thing because template representation are good in some sense. But for us, we care about other problem. So what I want to know is that if the Strichartz estimates works or not on locally symmetric space. But before to say that, I want to just shortly recall the PD motivation and what is a Strichartz estimate, why we care about it, and why it's interesting. So if we consider what time it is now. Okay, I still have 20 minutes. Okay. If we consider, we call the free Schrodinger equation means that it's a homogeneous equation with no with nothing on the right-hand side of this equation. And we know that, but do you have a formula? We know that the relation, the solution to this equation is given by this, like the Schrodinger semigroup acting on this function on the initial data. And then we can write it also as the kernel of this propagator with f, right? So the Strichartz estimates just want to know, can we control this solution in the time-space mixed norm by using the initial data? For the initial data satisfying some regularity conditions. Sure, it cannot hold for all the PQ. If it works for some PQ, we see that the PQ are admissible. So if S is 0, which means that the right-hand side becomes the L2, right? So in this case, we say that the Strichartz estimates has no loss of derivatives or has no loss of regularities. If s greater than 0, we have a Sobolev space with s strictly greater than 0. We say that the Strichartz estimates holds, but with loss of derivatives. And the last notation is just here. The definition of the time interval, if it's bounded, we say that the Strichartz estimates holds local in time. Otherwise, we say that's global in time. So it's well known that in the Euclidean setting, the Strichartz inequality holds without loss. It means that run height is L2, and the global in time, right? Global in time means that here is the hold unbounded time interval. And for all other miscible sites, for all PQ satisfying this condition, and this condition is sharp. But if we go move to manifolds, the first thing we know that a compact manifold, it cannot hold on R. I should be bounded because this kind of thing is bounded by U0 in some norms independent of T. So you cannot integrate it over unbounded time interval. So I must be bounded. And then Bourgain shows that on torus, S should be greater than the dimension over 4 minus 1 over 2. It means that here we cannot get L2. In two-dimensional if n equals 2, the right-hand side is 0. It means there is almost no loss, but there is still epsilon, right? And then Buch, Girard, and Tsvetakov, they prove that on a general manifold, on a general closed manifold, closed means compact without boundary, as they establish the Strichartz estimates with S equals 1 over P. It's not sharp, but it says at least that on a general compact manifold, you cannot get the Strichartz inequality without loss, right? So the question is, so on which manifolds the Strichartz estimates can hold without loss, without any loss? So there are many people working on that. Like for the PDEs, they prefer considering the so-called asymptotically hyperbolic manifolds. But for us, we already know that at least on hyperbolic space, the Strichartz estimates holds without loss. This was proved around 2007, 2008 by Eunice Staffilani, by Tataru, and also by Jean-Philippe and Pierre Felice. They already proved that at least on hyperbolic space, we know that the Strichartz, the global in time Strichartz, here is R, without loss holds. And the good part is that the other miscible site is considerable large than the Euclidean setting one, right? In the Euclidean setting, we know that the PQ should satisfy this equality. It means that PQ is on this line. But on hyperbolic space, we consider the point inside of this triangle, except for this dashed line. So this was generalized to all symmetric spaces, and recently by some collaborators of mine, and also both for wave and Schrodinger equation. We know that the symmetry space is such a space, is such a model, means that on symmetric spaces of non-compact, we have a global in time Strichartz inequality without loss. So the question is quite natural. We want to ask next, like, if it works on a symmetric space, so what happened on the corresponding locally symmetric spaces? It's natural but very hard to study. For this moment, at this moment, it's only known in rank 1 under some assumptions. This was proved by Buch, Guillermo, and Hassel in 2010, then by 3 Greek mathematicians. So the Buch, Guillermo, Hassel proved it on the real hyperbolic space, and Fodiatis, Mandualos, and Marias, they proved that in locally symmetric space of rank 1. They know that if the global in time Strichartz inequality holds without losing derivatives, without loss, then we know that the space should satisfy these three assumption. So the first is the corresponding symmetric space should be rank 1. And then the discrete subgroup should be convex co-compact. Convex co-compact means that the discrete subgroup acting on the convex whole of the limit side is compact. So when we talk about Anosov is just the higher rank concept of this notation. And they say that if this holds, we must assume that the critical exponent is small. But the problem these three conditions are not sharp, particularly for the second one. It's already known now if gamma, the discrete subgroup act in a way co-compact on a convex side, then there are only they're only the product of rank 1 copies or lattices. It means that in higher rank, this notation cannot provide enough interesting examples. So this is the main difficulty when we want to know what happens in higher rank. But this one is already thanks to what we because we already know in rank 1 we knew that if the critical exponent is small, it applies the temperances. Or now we know that in higher rank we can have the same thing, right? So this is important because with this temperances we can prove Kuhn-Stein phenomena, which holds in on semi-simple groups, but not hold in general, not hold in locally symmetric spaces. So that's why we need this. We started with the notation, but we still need the temperances here. So the main challenge is that how to get rid of the second assumption. This, if we want to know if the Strichartz inequality holds or not on a general symmetry space, on a general locally symmetric space, I think the second assumption is the most important to get right. So I think I stop here. So yeah.
You have still 5 minutes, I think 5, but you will stop here, right?
Yeah, I stop here. Yeah. Yeah, it's my last page of my slides. Yeah.
Okay, sorry. Actually, the thing is, okay, I will probably I will talk with you for 5 minutes after talk. Okay, so the thing is, yeah. So there are some examples. Can you have some examples of higher rank symmetric spaces? Okay, where you have calculated this gamma. Sorry, what is that notation? You have delta gamma.
Yeah, you can consider SL. You consider the SLN R mode SON as a symmetry space. Then you consider SLNZ as the corresponding
discrete subgroup.
discrete subgroup. But it's an example, not in our case, because in that case it's also a lattice. But there, exact. In my head, I think an exact example should be the product of two rank 1 symmetry space.
Okay, and you have calculated explicitly what is that, right?
Yes, exactly. Like you consider, the trivial case is like you consider the gamma 1, the rank 1 discrete subgroup, and you consider gamma 2 another rank 1 discrete subgroup. You consider product, but it's the trivial example. I think the non-trivial example, but you can compute explicitly, is you consider gamma as a discrete subgroup of rank 1 of the product of two rank 1 symmetry space.
Mm-hmm.
Yeah.
Can you show me the last result which you stated there?
Yeah, sure. I already stopped sharing, sorry. Wait a moment. Can you say it?
Yeah, this thing actually tempered. So what do you mean by the congestion thing? Here actually means you mean that
I didn't.
group you
Yeah,
have
it's
proved some
the
yeah.
it's the convolution inequality, like
Yeah,
the Young inequality in semi-simple groups.
but the thing is okay, you have
I
proved
can.
that temperedness in the, so means I understand that congestion inequality means you will get some more convolution inequalities, okay,
Yes, yes.
whereas which are stronger
I
than
can
Young's
share
inequality.
another. Yeah, I
But
can share
what is this?
another.
Yeah.
Yeah, maybe it's better. I share another picture. It's easy to explain it. Sorry, just a moment. Mm, So can you see the picture?
Yes. Yes. Oh.
Yeah, it's just constant phenomenon. I just means here the equation 1.88. It means that for G is unimodular, we can use the Young inequality, which means that all the points inside of this triangle, it satisfies the Young inequality. But the constant tells us if we take P between 1 and 2, we have something else. We still have this
This picture is nice.
inequality. Yeah, and we use the interpolation. We say that all the points inside satisfies this. So it's just the convolution inequality property in semi-simple groups. Yeah.
No, no, you didn't get my question actually properly, I think.
Sorry, I misunderstand your question.
This congestion property is the property of a group, right? This congestion, this thing, convolution
Yes,
thing you are
yes,
taking in group, right? So how
yes,
this
yes. For
discrete subgroup gamma is relate? What is this result actually? Last result. Basically, I am not able to
it's
understand this.
yeah. Yeah, it means that in general, the constant doesn't work on a locally symmetric space.
Yes.
So we should put additional assumption. So this
Okay.
temperedness is one of them. We need the temperedness to have the
Okay. Okay.
constant phenomena. Yeah.
Okay. This is only for sorry, locally symmetric spaces. This
Yes,
last
it
thing.
works on symmetric space, but not always true on locally symmetric space. That's why we need this temperedness condition. Yeah.
Okay. I understand. Okay.
Yeah.
Sorry. Actually, yeah.
No. It's
Okay.
my bad. Yeah, I didn't understand it at the first time.
Yeah.
Yeah. Yeah.
So maybe are there any other questions from the audience? Sir, you may end the talk seminar now.
Oh yeah. Anyway, you do that. Yeah. So there are no more questions. I think let's thank Hong-Wei once again. Thank you very much.